So this is a brief introduction to oxidation reduction reactions. So many of the reactions that we have worked with in chemistry already have been oxidation reduction reactions. We're going to take a look at a few examples here. Oxidation reduction reactions are unique in that electrons move from the oxidation reaction to the reduction reaction. So the oxidation part of the reaction, electrons are actually produced, and in the reduction part of the reaction, the electrons are actually part of the reactants. Because electrons are being exchanged in these reactions, there is a change in charge of the species within the reaction, and you'll see that as we go to balance the first reaction. Because there are electrons being exchanged, when you balance an oxidation reduction reaction, you're not just balancing the number of atoms, but you're also balancing according to charge. Now, balancing oxidation reduction reactions is a process of several steps, and we're going to go through those particular steps. Once the equation is actually balanced, just like in regular balancing equations, you can actually use the coefficients then through stoichiometry, or use it in stoichiometry, which is exactly what we're going to do. So let's take a look at the first example of an oxidation reduction reaction, and let's attempt to balance it. It's a very algebraic process. So we're going to take this particular reaction. This is permanganate reacting with iron plus 2, producing manganese plus 2 and iron plus 3. Now again, very methodical steps in the balancing of an equation, and the first step is to split the reaction into two half reactions. So when you do that, you want to make sure you include in each half reaction the same type of species. So in other words, I'm going to start with MnO4 minus in my first half reaction. So on the other half, I'm going to have the Mn2 plus. Then with the iron, we're going to take the iron 2 plus, and on the other side, the iron 3 plus. So in other words, we kept all the irons in one half reaction and all the manganeses in the other. And most of the time, it'll be pretty obvious which species go in the two different half reactions. Okay, so step 1, split. Step 2, make sure all the elements other than oxygen and hydrogen are balanced. So in the second reaction, we have 1 iron here, and we have 1 iron here, balanced. And we have 1 manganese, and we have 1 manganese. Now, for some reason, the elements other than oxygen and hydrogen are not balanced. This would be the step where you would want to balance those elements by just simply placing coefficients in. Second step then is to balance the oxygens and hydrogens. So we're going to take a look at the second reaction. So we have no oxygen or hydrogen here, and we have no oxygen and hydrogen here. So the second reaction we don't have to worry about. The first half reaction, however, we have 4 oxygens here, and then it looks like the oxygen has disappeared on the other side. Now the species that we have available for balancing, we're going to use water to balance our oxygen, and we're going to use H plus to balance our hydrogen. And we're going to do that consistently throughout the oxidation reduction reactions. So in the first half reaction, again, we have 4 oxygens. So to balance that oxygen number, we need 4 waters on the right side. With the 4 waters, we've brought along 8 hydrogen. So on the left side, we need 8 H pluses. So now when you look at that equation, it should look like the hydrogen, the manganese, and the oxygens are all balanced. So again, step 1, split into half reactions. Step 2, balance all elements except for hydrogen and oxygen. Step 3, if you need to balance hydrogen and oxygen, water balances the oxygen, and H pluses will balance the hydrogen. Step 4 then is to balance the charges on either side of each half reaction, and we're going to start with the second reaction first. So in this particular reaction, we have a +2 total charge here and a +3 total charge here. we are allowed to use electrons to balance the charge. So we're going to be putting negative in there somewhere to make the charges across the arrow equal. So on the right side, we are going to place 1 electron with a -1 charge. So that makes the right side a total of +2 and the left side a total of +2. Now the one above it is a little bit more challenging because we want to make sure we use the coefficients. So we have 8 positive 1s and then we have an overall -1. So our total charge here is a +7. On the right side then we have a +2 here and we have 0 because there's no charge showing on the water. Again, we're adding negative. Electrons are negative, so where would we add the electrons and how many to make the two sides equal? And hopefully you came up with the fact that we're going to put 5 negatives on the left side. So -5 plus +8 plus -1 gives us an overall +2 charge here, and then over here on the right side we have an overall +2. Okay, so again, step 1, split into half reactions. Step 2, balance all elements except for hydrogen and oxygen. Step 3, balance hydrogen and oxygen using water and H+. Next step then is to put in electrons to make the two sides, the charges, the same in each half reaction. And then the next step then is to make those electrons equal to each other through algebra. So we have 1 electron in this reaction, we have 5 here. And we want to do as little multiplying as possible. So we could do like multiply each of them by something, or very simply, we're going to multiply this whole second reaction by 5. And that will make it 5 electrons in each. Then we're going to add the two reactions together at the same time. So top reaction, 5 electrons, plus 8H+, plus MnO4-, plus our iron here from the second reaction with the 5 in front of it. And then on the other side, the top, we did nothing to it, so Mn2+, plus 4 waters. And on the bottom, we're going to have 5 Fe3+, and we're going to have 5 electrons. Now, notice algebraically, right? We have 5 electrons. I know it's a little hard to see there, but we have 5 electrons here on the left side. Forgot my negative there. And we have 5 electrons on the right side over here. So we're going to algebraically take those out of both sides. So we're left with 8H+, plus MnO4-, plus 5 Fe2+, producing Mn2+, plus 4 waters, plus 5 Fe3+. And that is our correct balanced equation. Now we could go in and do a real quick check. 8 hydrogen, 1 manganese, 1 manganese, 4 oxygens, 4 oxygens, 5 irons, 5 irons. And then the charges, 8 pluses, plus 1 negative, plus +10. And on the other side, a +2, plus a 0, plus a 15. So it looks like we have 17 total here, and on this side it looks like we also have 17 total. So if we wanted to do a titration like stoichiometry, we could literally do it utilizing these coefficients just like normal stoichiometry.